yesterday we spent quite some time looking at some examples of what I call fundamental models, so models that are supposed to be the exact answer to the dark energy problem, like quintessence or f of r or something. And then we started to look at the frameworks that group together large classes of models, and so we started with the effective field theory. So the effective field theory, even though the action that we get can be shown to be exactly equivalent to the Horndeski action, that was the most general the most general theory of single scalar field with at most second order equations of motion. The difference is that an effective field theory is not considered as a kind of a fundamental model. It's by design only valid in a range of energy scales, and outside it's not valid. So that's where we are right now. So I'll restart here, and then we will look at these two models, and maybe I'll say it now in case I forget it later. So the models we looked at here, well, obviously we did not look at all possible models, because near certainly not all possible models have actually been thought of yet. But also this class of models, as I said, it's equivalent to Horndeski effectively. There are also models that are not actually in here, like massive gravity, bimetric, non-local models. Those don't actually fit into this class. Okay. These here, they are parametrizations. They are more parametrizations of the observables, and so in that sense, they are fully general for cosmological observations. You cannot say anything about lab experiments, but they fully describe anything you can see in cosmology. So in that sense, they're more general, but they're maybe less physical, because you don't really know what the model is that you describe. Well, except, you will see. So we were talking about the effective field theory, and here is the action. So this is one form, this is another form, and so once you have an action, then you can just use this machinery that we discussed yesterday. You can calculate equations of motion, you can calculate stress energy tensor at any level in perturbations that you want, and you can work with that. So once I have given you the action, I can tell you, please go and look at it and come back in a week and tell me what you find. So that totally specifies the model, except that in this model there are these three functions, and these three functions, again, we should think of as parameters that describe the kind of material or the model that we are looking at. And so in the context of fundamental actions, you would kind of like that your fundamental theory will fix these parameters for you, while in the context of effective theories, these are quantities that you should then go and measure. Of course, the difference to some degree is philosophical, especially because you have exactly the same action between Horndeski and this one, and then it's just the interpretation that is a bit different. But especially in this form, so this is the same action just rewritten, but in this form you can then make a list of what these quantities are. And so, well, h of t is just a Hubble parameter, and as I said, so I quickly already discussed this, so the alpha k, that is effectively the kinetic term, so it's what determines your sound speed and therefore the sound horizon. The braiding, that's a bit a strange term that people try to avoid thinking about, but I think it would be interesting to look a bit more at that. The Planck mass run rate, so this parameter alpha m is the derivative of m with respect to time. This tells you about non-minimal coupling, because typically you get the running of the Planck mass if in the Einstein-Hilbert action, instead of r, you have phi of r, so typical for a scalar tensor theory. And in that case, if phi evolves, this is exactly a running of the Planck mass. So that's what this term gives you. As I said, this here, if you calculate, because if you have the action, then you can not only calculate your scalar equations, that's everything that we have looked at was about the scalar degrees of freedom, but you can of course also calculate the equations for your tensor degrees of freedom, and the tensor degrees of freedom, that's gravitational waves. And when you, actually there are many things I should be telling you about that part, that sector, but I don't have the time. But it's especially interesting also because now we see gravitational waves. And but for example, yeah, this parameter that tells you directly the speed of gravitational waves. And as we now know, the speed of gravitational waves is very close to the speed of light. So for all practical purposes, you can forget about that part. And actually, that also has consequences elsewhere, but that's a bit more subtle. This one, by the way, this parameter enters in the friction term for gravitational waves as well. And so that means that if you have a running of the Planck mass, then you could see differences between standard candles, between electromagnetic standard candles, so luminosity distance to supernovae, and gravitational wave standard candles, so standard sirens. They wouldn't actually show the same distance in that case. So you could use these measurements to put constraints on that. That's, however, not something I really have time to talk about, so we could give a whole lecture about these. These terms I will generally neglect. These are terms that look like they are higher order in the equations of motion, but when you actually calculate the equations of motion, then there are constellations that make them second order. But these probably are ruled out by solar system constraints. But these are really questions people work on. So this is really at the front of the research. Okay, I already said that these are the property of the material, and in addition, that was already also pointed out by some of you, there are also additional conditions, because if you look at the speed of gravitational waves or the sound speed, if that one is ever negative, the sound speed squared is negative, as we discussed, it's an instability of the model, and there are also other instabilities. You need a positive kinetic term. Well, whether you need it or not is a bit open to debate. But in general, negative signs in front of kinetic terms are considered awkward. That's called a ghost. And there are codes that implement this. Actually, high class implements this scheme. EFT-CAMB implements the other scheme, but I think you can now also use this scheme. I find I sound funny. Is it okay how I sound? Nothing to do with alcohol. Yeah. But can you hear me well, or should I replay it? I'll just complain. Okay. And so here is, for example, here is just to show. Then you have, if you look at some of these models that I discussed, that we can think of as fundamental models, then here is how they fit into this parameter scheme. And so, for example, quintessence has a very specific form of the kinetic term, and all the others are turned off. And k-essence is a generalization of this with a sound speed that can be different from the speed of light. And me personally, but for reasons that I probably will have to explain in the coffee break, I consider these parameters dark energy parameters, and those parameters modified gravity parameters. But it's not easy to give hard distinction. Are there any questions about the EFT side? It's a very compact introduction. But now I actually want to talk a bit about these two. Now these two, you can show that these two approaches, they are exactly equivalent. So you can always. Okay, but actually we have already discussed this. So in principle, you already know this. So from here you can always predict these parameters, but it's harder to go from these parameters back here. And not all of these parametrizations have an equivalence here. But so we can always go down, going back up is harder. Okay, so what do I mean with equivalent fluid description? Well, this is simply what we already discussed, that if, let's say, I have a quintessence model, then for each potential I can solve the equations of motion, and then I find what is my equation of state as a function of time. And so the fluid part is that I can describe this model in terms of the fluid equation for a given W. I don't actually need to solve the field equations, I can just solve the fluid equation and choose W. And that's what I mean with the fluid model description. And so because typically what do we do? Right? Typically if we measure W, we don't work with an effective field with some field theory model. Rather we just observe stuff, and what we observe, so typically that would be distances. So if we observe a luminosity distance or an angular diameter distance, we get a constraint on this integral, and so we get a constraint on the expansion rate, and this effectively determines the left-hand side of the Einstein equations. And if we know the left-hand side of the Einstein equations, we also know the right-hand side of the Einstein equations. And then we can look in here, what is the pressure, because we can basically, in terms of these equations, we can write them as the Friedmann equation and the conservation equation. So if I know the evolution of h, so if I know the distance, I can find the evolution of h. If I know the evolution of h, I can find the evolution of rho. And if I know the evolution of rho, well, then I can find the W, and the W tells me what I have. If W is 0, I have matter. If W is 1/3, I have radiation. If W is -1, I have cosmological constant, right? And if W is negative but not -1, then I have some kind of dark energy, dynamical dark energy. And so here is just another way. So I'm telling you the third time the same thing, so this is really just the same. And just to say, okay, what we really measure here is the P or the W. This normally we call the background. That's the exactly homogeneous and isotropic part. And so basically the W plugs in here, and then we can close this circle. And with the observables, fix H. Okay. And but as I mentioned, we can also do this at the level of perturbations. And so with the level of perturbations, now we have phi and psi. If I look at the scalar perturbations that are important for structure formation, and then we have the Poisson equation and the equation for the anisotropic stress. These are the Einstein equations. And then we have the conservation equations for delta rho over rho and for the velocities. And so you see now, as we already discussed, so you see I already did all the dark energy stuff while I was pretending not to. There are two quantities here that play the role of W, so you can think of it as the delta P. The delta P can be translated into a sound speed and this anisotropic stress sigma. And so if you fix these, then you can solve, let's say in the forward way, you can then solve your conservation equations and plug it into the field equations, and then you know what phi and psi are, and that's what tells you what you observe. And the other way around, if you start from observations, you can use the observations to determine phi and psi. That's the geometry side, and then the Einstein equations, they link phi and psi to the evolution of delta and the velocities, and here directly sigma. And then with the conservation equation, you can then uniquely determine what delta P and what sigma is, no, because we have 6 unknown variables, phi, psi, delta, V, delta P, and sigma, 6. We have 4 equations. Oops, okay. Some random order, we get 2 left, and these are these 2. Okay, and then maybe you say, well, that's great, does this actually work? And it does actually work, just not for dark energy at this point. I mean, it also works for dark energy, but we only get limits. But in some cases, we actually get detections because we can use this since this can describe any material, we can use it to look for something that we know should be there. And one example would be neutrinos. Neutrinos, they are like radiation, and so they should have a W of 1/3 and a delta P that is given by a sound speed of 1/3 and a sigma that's given by kind of a viscosity of also 1/3. And it turns out that one can actually measure this, and so here is a plot from Planck. Forget the preliminary, I was just too lazy to replace it with the plots without the preliminary. So this is not preliminary, okay. And so here you have a sound speed. Here you have the sound speed of the neutrino background as determined by Planck, roughly at the time of recombination. And you can see that it is consistent with 1/3 and a very clear detection. So this is a direct measurement of the neutrino background, of the anisotropies in the neutrino background through the CMB. And you see, what you do is you can determine these parameters, and so then you can check what this is, and this clearly tells you see something that behaves like a radiation fluid. And the interpretation is that these are the neutrinos. So in principle it works. And you can also do this for things that are not dark energy. For example, you can test your dark matter. Is your dark matter actually pressureless? And so then if you just basically, normally when you, in your code, when you describe dark matter, you put in by hand, W is 0, delta P is 0, sigma is 0, but then you can add in these parameters and look what constraints do you actually get. And so you find that W is of the order of 10 to the minus 3, so the pressure is much less than the energy density. Of course, the expectation here is that this should actually be a huge number. But nonetheless, there is no pressure detected, and the sound speed is 0 up to 10 to the minus 6, and this viscosity contribution is also 0 up to about 10 to the minus 6. Okay, so as far as we can see, dark matter behaves really like dark matter. You can actually get stronger constraints on dark matter from different probes, but okay, I'm not talking about dark matter, but you can ask me about it. Okay, so this is what I mean when I say fluid description. So since this fully parameterizes the scalar perturbations of the geometry, this can describe anything. The price to pay, that maybe I did not communicate very clearly, because as a salesman you want to sound good, is that phi and psi, they're function of scale and time. So here we have, before we had 6 functions of time, while here now we have functions of scale and time, so 2 dimensions. And of course that's a much bigger space than just functions of 1 dimension. It's infinitely bigger. Okay, that's a bit unfortunate, the price to pay. Okay, and then instead of parameterizing the fluid, well, we can also directly parameterize deviations in the observable, let me call them observable, in the geometry. So instead of introducing a fluid, we can just say, well, actually, normally we have a Poisson equation, and I say, okay, here I put the matter, but if I have a dark energy that clusters, I have an additional contribution, and instead of putting it in as an additional delta for which I write down fluid equation, I just put the parameter here that can be different from 1. So in lambda CDM, this parameter here would be 1 because there is only matter here, but if there is an additional clustering component, or if the gravitational constant changes, evolves over time, if the Planck mass evolves, then I get some additional parameter here. Okay. And then I can do the same. So in lambda CDM, phi and psi are the same, and in other models they are not, and so I can just introduce a parameter that parameterizes this difference. And so then you can show that this approach, where I directly parameterize the deviation of phi and psi from expectations if there is no dark energy, is exactly equivalent to the fluid approach. You can go from the one to the other, and from the other to the one, and you can write down equations. Okay, so generally at low redshift we would then expect mu and eta equal 1. Why do I write low redshift? Because normally, well, firstly, if you go to high redshift, you should include radiation here. And secondly, specifically for the eta, at high redshift we saw that the neutrinos, they gave you this viscosity contribution, and this will actually give you a non-zero eta contribution at high redshift. But normally we can neglect that. And then of course, when we come from the fundamental models, we can predict all of these quantities. And so just to give you some examples, so this is an old slide. So the Q is a bit like the mu, just not quite. I should say that there are many, many different ways to do this, but you can see in the DGP that I briefly mentioned yesterday, this 5-dimensional model, you get the deviation in the Poisson equation of about 30% at late time, and also the eta has a change of about 0.4. So this is a modified gravity model. So modified gravity model generically can give you order 1 deviations in these parameters from the expectations. Okay, and here is some expression for a scalar tensor where you have similar sized effects, and you already saw what the Q, except for the psi potential, is in k essence, but in k essence eta is exactly 1, and on large scales the mu, so the additional clustering is around 4%, but on small scales it goes away. And so you can see that dark energy tends to have smaller effects, and modified gravity tends to have larger effects in this parameter. Good. Okay, but today I really wanted to go to the last point, and then these are really the observations, and so then to use the observations to put constraints on these models. And so what's the basic idea? So here is also an old slide. How do we measure things? So here what I haven't actually really mentioned is that, well, I have mentioned it a long time ago, that if our model breaks the cosmological principle, then we can do things. So this here more or less says that we can put constraints on curvature, but also on violations of the cosmological principle from measurements of the expansion rate and the distances, but this I didn't really discuss very much. But then using background data like supernovae, in principle we can constrain W, and then we have phi, psi, forget the bias, delta m and Vm, and so to measure those we need to have, what we really want to measure is phi and psi, and so the important part really is this. And so effectively, if you look at maybe I should actually put, I can dig it out if you want. If you look at the geodesic equation, so how particles move, you find that light is accelerated by phi plus psi, so gravitational lensing measures phi plus psi, and the motion of particles measures psi. And so the two key observables really for us is gravitational lensing and measurements of the velocity field, typically through redshift space distortions, that I will discuss in a moment. The galaxy P of k, the problem is a bit that galaxies cluster not necessarily the same way as the dark matter, so it's not always totally obvious how to use them. But the other two are very clean terms, as far as we know. Okay, so now we're going to look a bit at data, and I will go in a bit more detail through the data, and so maybe I don't want to discuss this slide right now and just hop in. And this is just to say that since I am or was in Planck, I have to say that I'm not personally Planck. There were two, three other people doing unimportant work on this data set. No, I was a fairly unimportant person. Okay, so what are we going to look at? So let me maybe discuss a bit the data, so everybody who knows it can now have a little nap. And so here is the CMB. Who doesn't know what the CMB is? Everybody knows what the CMB is. Good. Maybe I should have asked who knows what the CMB is. Okay, so let me just quickly say, so at some very early time, like the universe in the past was was smaller, and so everything got compressed, and so it was also hotter, the radiation density was higher, and if you heat stuff, at some point it gets ionized, and that's what happens at the temperature of about 3000 Kelvin in the universe. And if the universe is ionized, then you have free electrons, and free electrons are very good at scattering photons, and so above a temperature of 3000 Kelvin, the universe basically stops being transparent. And so it's like, and if you run it forward, the universe is not transparent, photons get scattered all the time, then the temperature drops below 3000 Kelvin at about 400,000 years, and the universe becomes transparent suddenly, and the photons propagate to us. And so if we look out, we can look up to this wall of fog. Okay. And so if we take pictures at the right frequency, namely at the temperature at which the photons arrive on Earth, then we see exactly this wall of fog. What is so this happens at about a redshift of 1000, and this means that the photons are about 1000 times cooler, so they're a bit less than 3 Kelvin. Okay, so what do we see when we take the picture? Forget the text. So what we really see is this. And this means that the sky is uniform and has a temperature of 2.73 Kelvin. Okay, and then to actually see anything more, we have to subtract this uniform component, and then we see this. And who knows what this is? Dipole, yeah. So this is a dipole, and this is thought to be because of our motion with respect to the CMB. So the CMB in some sense defines a preferred frame, but we are not at rest with respect to that frame, so we move through this photon field, and that gives us a dipole. And this one has 3 millikelvin, so that's 3 Kelvin, 3 millikelvin, and now then we subtract this dipole, and then we get that, and then we are at 10 microkelvin. And so what is this? That's the galaxy exactly, and so we don't really want the galaxy, we want this stuff around, and so you have to subtract this, and then you need to build a bit a newer detector, and then you get that. Okay, and so this here, and this is actually a bit cheating because you cannot quite subtract it in the middle, but it looks nicer. And so this is a picture of the universe when it was 1,000 times smaller than today. And then, as I already mentioned, we think that this is a Gaussian. Actually, you can test it, and it looks like it's an isotropic Gaussian random field. And that means that you can fully describe it by the power spectrum, the 2-point function, so the variance. And here is this variance as a function of scales. So these are small scales, these are large scales. This L is a Fourier transform on the sphere. And so here is data that's already a few years old. But you can actually see that we have a very nice data that very nice sees a curve, seems to trace a curve. And there is actually a curve on this plot. And this is a 6-parameter fit to all of this data. Okay, that's actually quite impressive. I mean, you can say, okay, with 6 parameters you can fit everything, but my thesis topic cannot fit that. So topological defects, they can totally not do that. Okay, and also it's kind of also interesting just to say, so you go from time-ordered data, you go to this map. From the map, you go to the power spectrum. And these are maybe 50 million pixels, and here there are several thousand numbers, and because of Gaussianity and isotropy, you shouldn't lose any physical information. And then you can, these several thousand numbers, you can then describe by 6 parameters. And this is a gigantic compression. And that this works is also a bit surprising. Okay, so how do you then measure anything? So here is some animation by Wayne Hu. Well, when you vary these parameters, your curve moves around, and then you just look what's the best fit, right? And some of these things are easy to understand. For example, the first peak is a compression peak, and the second peak is an expansion peak, because what you really see are sound waves in the radiation fluid in the early universe. And so if you have baryons, normal matter, basically the protons and electrons which are coupled to the radiation, So they have self-gravity, and so when you have an overdensity, they actually compress the fluid more. And when you have an underdensity, they try to resist the expansion because of their gravitational attraction. And so if you increase the baryons, you increase the compression peak and you reduce the expansion peak, the underdensity. And so that's a way to measure how many baryons you have. And then if you change curvature, then you change the scale under which you see a given, or you change the angle under which you see a given scale. And you can see that if you change curvature, your peak position moves to different scales. And so that's why the CMB is very good at giving you this very sharp constraint. It's actually not exactly the curvature, it's a bit tilted. And okay, so here is just the newest data because the previous figure was not very new, it's not very good. And so here you see again the model, and you see the curve goes through these data points very nicely, and you can look at the residuals. And apart from these data points here that don't have a lot of statistical weight, this is actually, statistically speaking, an acceptable fit. So there is nothing that looks extremely funny in this data. And then you can take this model, so these are the temperature anisotropies, but the cosmic microwave background is also polarized, and the theory tells us how it should be polarized. And so we can calculate in this model, without additionally fitting, how it is polarized. Okay, let's not look at the text again, let's just look at the figure. And so you can measure the polarization, and you can plot the curve that should be describing the polarization. So this is the polarization, and this is the cross combination of polarization and temperature, and you really see that they are nicely, that the one fits nicely the other. So that's also just another point. So this peak here is outside of the horizon, and it's very, very hard it's outside of the horizon at last scattering, so when the CMB was created. And you can change the temperature at late times, but it's very hard to change polarization because you need to scatter your photons. So you need to rescatter all the photons at late times in order to generate the polarization here. And so the fact that we have a peak basically tells you that something acted on scales larger than the naive causal horizon. Okay, that's not dark energy. Still, I think this is an amazing observation. And then these peaks that we have here that come from these sound waves in the early universe. So as I just said, well, the baryons are dragged along, and so these peaks are also imprinted in the baryons. And okay, here is an animation that will probably stop after. So you can see the baryons and the photons moving together. Photons move away after recombination. Baryons are stuck. This is the dark matter. And then the dark matter falls into the baryon potential well, and the baryons fall in the dark matter potential well. And so that gives you a preferred scale. Oops, that just disappeared again, which is linked to the CMB peak scale, and you can actually see this in the data. So when you look at the galaxy distribution, you see oscillations around the smooth curve, and these are these BAOs, these baryonic acoustic oscillations. And this oscillation scale is directly linked to the scale that we observe in the CMB. And so this is because of this is the combination of CMB and BAO is a very powerful combination. And so here you see again, you see it in real space where you have this preferred scale again, and it's a size of about 150 co-moving megaparsec, which is nearly linear. Okay, because theorists are stupid. We only can do linear calculations, so that's why stuff like HEN and similar things, they're really hard because this is not linear. But whatever is linear, we can actually calculate. And so since this is nearly linear, we can more or less calculate it, and we are more or less confident that what we get is right. And so here you see some data points relative to the prediction of Planck. When I say prediction of Planck, Planck effectively mostly measures the universe at very early times, and then in order to make predictions for late times, we need a model. And so what we do here is we use lambda CDM to predict, to move the Planck measurement forward. And so if if this agrees with the Planck curves, then it means that lambda CDM is potential, is at least not obviously wrong. And if this disagrees, then that may be a problem for lambda CDM, or it may be a problem in the data. And so, for example, you see that there is one peak that is off, one data point that is off, but at the moment, most people, me included, tend to just drop this data point out because we're not sure what to do with it. Since the data fits here, it's very hard to kind of get friends. Okay. And so here you see some measurement. So this is BOSS data from the CMB, from the galaxy clustering SDSS survey. And so you see this direction here, so this is at the redshift of 0.38, 0.51 and 0.61, and the BAOs, they measure in the radial direction, they measure the expansion rate, so these are measurements of the expansion rates at this redshift there, and in the transverse direction they measure an angular distance, and so these are measurements of angular distance, and so this is the correlated contours from these data points, and this is the Planck prediction. And you see the precision of the Planck data, how it cuts through here in a very narrow way. You can probably barely see the Planck contours. But nonetheless, even though they are very sharp, they get cut off out here by the BAOs. So the BAOs do add significant information. And here is a plot where you can actually see, you remember that we had these different distances. No, actually that's not true. So what we plot here is the angular diameter distance, which is here. This is the expansion rate data point, and this is some averaged because some of the BAO measurements they cannot statistically measure separately the radial and the transverse, and they average. And so this is kind of with the data points that we have. And so this BAO, this is one aspect of the galaxy distribution. But yeah.
All these data points are from BAO data points. Some so do you classify these results as a consistency test for the CCE or a real test?
That's maybe something I would like once to ask a master student to study a bit. So the groups who do it, well, they do it with respect to a reference model, but then they include the reference model in the way the likelihood is phrased. So in principle, deviations from the reference model to some degree should be correctly reflected. But if you go too far away from the reference model, then it's probably no longer correct. But as long as your data is not too far from lambda CDM, it's probably okay, but it's scary, I agree with you. So actually nearly all of these measurements need some reference model somewhere, because, let me just quickly try to go back. Because when you measure this peak here we have a physical scale, but we don't observe also physical scales. We need also a model to translate angles into physical scales. And so, but in principle, you wouldn't need to do that, but in practice, everybody does it. Yes, and I think it's, as long as you don't observe big deviations, it's okay. If you did observe big deviations, you would have to redo the analysis, I would say. But I would not be able to give you an exact quantitative statement. But yes, it also makes me unhappy. But the CMB is significantly more self-consistently analyzed. So not totally, but nearly. I mean, the CMB itself is pretty much completely self-consistently analyzed, but the CMB lensing needs some corrections that are again calculated in the model, and my colleagues assure me that they checked that this is not significant for any reasonable deviation, like quantify reasonable. Okay, so what we see here is the 2-point function in transverse direction and in radial direction. So basically you just plot the density of galaxy pairs, and you see that galaxy pairs like to be at this distance, which is this 150 megaparsec. It says 100 because of the 1/h. This is this 150 megaparsec BAO peak. Okay, so this is the BAO scale. And then you can zoom in and look at pairs that are closer together, and then you find this pattern, and this pattern shows two different effects. One effect is that on large scales, if I have a like galaxy cluster, some overdensity, some potential well, then galaxies around it are going to fall into it. Okay? And so if something is here closer to you, but it falls away from you, what happens to its redshift? So what's the Doppler? What does the Doppler effect do? Yeah, so it's redshifted, and so it looks further away from us. So the Doppler effect therefore effectively will move it to somewhere here, just because of so if you use redshift to infer a distance, and the galaxy behind us, so we are somewhere here, the galaxy behind us is falling towards us, so it's blue shifted, and so it looks closer to us, and so the Doppler effect moves it to somewhere here. And so if we look at an imaginary circle, this circle will be squashed, right? Because galaxies here, they have a transverse velocity which gives no redshift or blue shift, but the ones that are directly before and behind, they are moved away if they are in front, and towards us if they are behind. And so this circle here, if this is a circle, it actually becomes squashed, some kind of ellipsoid. And this is the squashing you observe here. And then in addition, galaxies that are very close and that have actually already fallen into this gravitational potential, they start some random motion, they're virialized, and if you have a random velocity dispersion, this gives you a broadening. And so this is the broadening in the very center that we see there. So the broadening is highly nonlinear. We don't know how to deal with that, but we can more or less predict the squashing part. And so the squashing part is what is called redshift space distortions. And so this squashing part, this squashing tells us about the velocity of galaxies, and through the velocity it tells us something about the potential wells. So this tells us something about this psi potential. Okay, and so here is the current data sets measuring some specific combination. And compared again to the Planck predictions, and you see that it's compatible with the Planck lambda CDM, but the error bars are fairly big. And also here you need a reference model, but here then the reference model is encoded in the so-called Alcock-Paczynski parameter that maybe I don't get into it, but you can also see that this is the Planck data cutting through here, and these are the Boss data points, the same one as before, but here it's the redshift-based distortions that were measured. And you can also see actually the dotted curve and the solid curve that those who are in front can see. They show two different analyses, both by the Boss team, so by subgroups of the team, and so this gives you also a bit an idea of the systematic uncertainties in these analyses. And so, okay, so now we had CMB, we had redshift space distortions to measure velocities or the psi potential, and the third important ingredient is gravitational lensing. And so, as you know, if you have mass, that deflects the path of photons, and so here is a nice picture where you see these giant arcs. Okay, this is not the lensing we are dealing with. We have much more boring pictures with tiny deformations that are totally invisible and that you can only get statistically, and this is then called weak lensing. But the principle is the same. So if you have some massive, some strong mass here, the photons get deflected, and then you get deformations of pictures. And this, since gravitational lensing is determined by phi plus psi, this tells you something about phi plus psi. And so here is a not very up-to-date plot, but more or less, of the lensing data. Here I'm a bit nice to Planck, because I use the DES lensing, and DES agrees well with Planck. There is another data set, KITS, which agrees a bit less well. That's a discussion we can also have over coffee. But you can see, so in my opinion, it doesn't look very, the blue is the Planck inferred, what Planck expectations for what they should have been seeing, and so they agree relatively well. And then there is one subtlety that normally I wouldn't be telling you about, except that it will become important in the constraints. And that is that Planck can measure lensing in different ways. So one thing that happens is that when you measure the anisotropies, the lensing remaps slightly the pixels that you measure, and that gives you a smoothing effect on the power spectrum. So the Planck power spectrum always has lensing. You cannot remove it. And but you can try to measure it, and that's the black curve. Black 1 is what you would expect, and so you see the black PDF, so this is the probability distribution, is higher than 1. And so somehow the Planck data is Planck power spectrum is a bit too smooth. But you can also measure, this remapping gives you also higher order correlation functions, and so you can use those to measure it directly, and this is the red curve. And the red curve is statistically consistent with 1 and lower than the black curve. But these are both Planck data, so this cannot be a physical effect that is between them. So this means that somewhere in the Planck data there is also a systematic effect that we don't understand. But if you look at the power spectrum, and if lensing is important for you, you will prefer models that predict more lensing than what lambda CDM will predict. But if you add the lensing extraction, then it will push you back again, because that one is stronger and doesn't see that excess to the same degree. And we will see this effect later on. Okay, and so this is just to show this is the lensing potential as measured by Planck, and that's about the 40 sigma detection. And here's the plot I stole from Beth Reed. That just shows you a bit, okay, we are here, you are here, and you look out. And so this is SDSS galaxies, so that's where you measure the BAOs, and you measure the redshift space distortions in these wedges. This is the main sample. SDSS also looks at Lyman alpha, but we don't really use the data here, but you have data a bit further out. And then very far away is the CMB surface of last scattering. This is probably using distance, not redshift. If you did redshift, it would be much further out. Okay. But this gives you a bit, kind of the global idea. Okay, so now finally let's look at the constraints. So we start by using an effective quintessence model. So you know now when I say effective quintessence model, I take the fluid equation that corresponds to a minimally coupled scalar field with a standard kinetic term, so sound speed is 1, and sigma is 0, and I only constrain W, and that's what normally people call dark energy. And so here there are two parameters, W0, WA, that parameterize the equation of state, and if W is -1, which means W0 is -1 and WA is 0, then you're consistent with the cosmological constant, and CMB data alone is very bad at constraining it. So the posterior here is shifted, but that's just a prior effect. You really need to add either supernova BAO, actually that's the strongest combination because that gives you really a background constraint, but also redshift space distortion, weak lensing push you back to this point. And so you can see here we are nicely around the lambda CDM point when we have this data. There is no significant difference detected. And the shaded region, or rather the non-shaded region, these are models that never go below -1. Because a normal quintessence model would never go below -1. And so if you want to only look at the others, then it's like this little corner here that is allowed. But as I said, everybody else has nicer plots, and so we also cheat. Okay, and if you only allow for a constant W, then you get a very strong constraint. And this also shows you that if you parameterize, and we will also always parameterize our free functions in some way, the constraints you get depend strongly on the parameterization. This is a very important point that I didn't mention before. So choosing how to parameterize this is kind of a bit of a black art. And the way you choose it strongly impacts your result. And of course, there are models that you cannot parameterize in this way, and so those are effectively just invisible. Okay. I have so many nice things. Actually, this isn't the next. This maybe I don't really need to mention. That's not very relevant. Okay, and actually, so because of this problem with choosing how to choose the parameterization, you can also try to reconstruct W as a function of redshift. Here we actually admittedly use the same parameterization, but it will give you these contours, and then instead you can do it in redshift bins, and we also tried more bins. We also tried higher order in this paper. This is the 2015 dark energy modified gravity paper, but there is no deviation visible. And I think that's the consensus in other papers is the same. So at the level of dark energy, when we look at the background, there isn't really any deviation. There is a little small print. If you impose the high H, then you are pushed a bit away from that. But that's I think that's a bit on the speculative side. So this is the dark energy, and then our modified gravity model that we looked at was f of r, and here is a constraint on f of r, again from the 2015 dark energy modified gravity paper. And here we use a lambda CDM background, and you remember, probably not, I said very quickly, if you use lambda CDM background, you have an equation that is fixed except for initial condition, and here effectively we put the constraint on the initial condition, and if this parameter is 0, then we are in lambda CDM. So the more we go to the left, the closer we get to lambda CDM. And so this is again the PDF. And so you can see that as you add in especially BAO redshift space distortion, but also V-cleansing, you are being pushed more and more to the left. Okay, and so the final constraint is of the order of 10 to the minus 4 in this parameter. And so then it's hard to say what would be a natural value for this parameter, but as you get pushed to lower and lower values, you start to wonder how relevant this still is, right? Because you're really pushed more and more towards models that look exactly like lambda CDM. So f of r type models don't see deviation from lambda CDM either. And then we try the effective field theory of dark energy. And so, okay, so this is actually the discussion I already had earlier. So this is, so in principle we have all of these parameters, but in practice, so this is actually the tensor equation now. This is not the scalar equation, this is the tensor equation. And so here is the speed of gravitational waves, and we know that this one is 1, and this would be the friction term that I didn't write out in detail. And this effectively turns off the alpha t. And then if you look at the models in more detail, you find that either you have to fine-tune things, or you have a dark energy type model, or you have an additional constraint on alpha m and alpha b. And so we also implemented this constraint, and this effectively turns off now most of your EFT metric, your EFT action. And now you can pretty much parameterize everything just with this Planck run rate. And so this is effectively a non-minimally coupled K-essence model. And so now we just measure this alpha m, and we parameterize the evolution of the alpha m. This is a function of time. We parameterize it in a specific way, more or less. So this omega here is the relative contribution of the dark energy, and so we parameterize it. That this should act like basically that the relative contribution of this modified gravity of this model, that it scales like the dark energy density, so it turns on at late times. This is again a specific choice. We somehow always end up with specific choices, but there are also more comprehensive studies in the literature with results that largely agree with what I'm telling you here. So there isn't really anything else happening as far as we know somewhere else in parameter space, but it's something that should be tested. Okay. And so here here we see the PDF. 0 means no detection. And then now if you look at Planck alone, without any other data, you actually get something that looks like nearly a detection of something. It's a bit a surprise that it's negative, but whatever, okay. And the delta chi-square is about 10 for one extra parameter. So an improvement in the chi-square by 10 for one extra parameter is quite, actually not 2, sorry, 2 extra parameters, but we could hide one. This is actually quite good, but we are very sure that what we see here is actually this lensing in the CMB spectrum. And when we turn on lensing either by the CMB lensing or with weak lensing measurement, then we are being pushed back. So this would be the solid or the other dashed contour, and you see those are nicely consistent with 0, and the delta chi-square goes down to about 2 or 3, and that is not a significant improvement, especially not for two additional parameters. So we don't see any EFT type deviations either. And so then we can look at these phenomenological parameters mu and eta, which can be mapped on the fluid parameters, but we didn't actually run a fluid case here. And okay, so just to remind you, the mu tells you additional clustering, and the eta is the difference of the two potentials. And so the combination of, so this actually is strongly constrained. I think I will show this in the next slide. This one is strongly constrained by redshift space distortions, and the combination of these two is constrained by lensing, and I will rotate parameter space in a moment to make this more clear. And so we also parameterize these functions by neglecting any scale dependence. We checked if we can see any, we can't see any, but the errors blow up, so we decided not to put one. And at the time evolution, we again parameterized to be proportional to the dark energy density. And what you see here not very well, because here we always have the lensing in, is that it's slightly shifted up, but it's pretty much consistent. Actually, do I have the old plots on that? Not really. And this is the latest parameter paper in 2015. We also didn't use the lensing. I mean, we also this time didn't use the lensing, but if you don't use the lensing, you get exactly the same problem as in the EFT. You get pushed up because your model wants more lensing. And again, if we don't put the lensing, if we just put Planck and PAO, we get the delta chi-square of 11 in this case. But this is effectively the identical effect to what we saw before in a very different framework. And actually that's also nice, that analyzing it with EFT, with the EFT scheme, or analyzing it with the phenomenological parameters, sees the same effect. So if we believe that this was actually a signature of modified gravity or dark energy, we would have found it with both ways. Sadly, we don't think it is. We think it's a systematic effect in the Planck data. But it's nice that we see it twice. You know? At least it's consistent. Okay, but you can also see how the parameters shrink down. You can see that currently, I won't really have time to talk about forecasts, but let me maybe just tell you the forecasts right here. Currently, the uncertainty here are of order 1. Okay. And so within the next 10 years, roughly, that should shrink by 1 or 2 orders of magnitude in each direction. So we should end up with contours that are about this size after Euclid or LSST. Okay, so here is a bit more physics. I'll explain a bit more what we are seeing and why we are seeing it. Well, here actually you see one of the old contours. You should forget the weak lensing part here. You can ask me why I say that. So see, the old contours, they were roughly 3 sigma out from the lambda CDM point, but that was because we don't have lensing. When we add lensing, we get shifted in. So these are the 2015 contours. What I just showed you were the 2018 contours. Okay. And then what you can do is you can actually look at the models. You can you can take your best fit model and you can calculate your CMB power spectrum and your lensing spectrum. And so the solid black curve here is lambda CDM. And what typically happens when you turn on one of these modified gravity type models, you get a huge what is called ISW effect. And that's what kills most of these models because Planck doesn't see it. Actually, the CMB has a long-standing problem that it sees too little power on very large scales. And so it turns out that if you play around with your parameters, you can have models that predict less power. And so this dark blue dashed curve has actually less power than lambda CDM. And actually the CMB likes this, but it's not very statistically significant. Okay. And then in the lensing, lambda CDM predicts this lensing, and most modified gravity parameters give you more lensing, some give you less, okay? And then you can actually find models, or rather the data finds models for you, where you not only suppress the ISW effect, but you also increase lensing. And so this ticks two boxes as far as the CMB, the Planck data is concerned. It has a bit less power on large scales. CMB generically likes that. It has too much lensing. Planck data likes this. And so that's why this model is the preferred model by the Planck data. But then when you turn on additional lensing data, then the lensing data wants to go back to that and kills those models. And so we understand very well why we see what we see. And I'm not sure if I really wrote it. But okay, here you see a bit the same effect again. So here, these sigmas, the sigma is the combination of eta and mu that fixes that tells you about the lensing, and it's effectively what here is what is the vertical scale here, except here is the deflection angle, but it's effectively the same. And so you can really see how your lensing goes up as you move in this direction. And that's why these models are preferred. And here you can also see a bit what the data sets do. So this is the Planck data set. This is the lambda CDM so if you impose lambda CDM, Planck says you are here. If you allow for these parameters, Planck goes up there. This also shows you the importance of a model in cosmology. If you fix lambda CDM, you get this. If you allow for a more general model, you get that. Okay. But then you can see that as you turn on lensing, the CMB lensing, you go from the blue to the red. So you get crunched down. If you turn on DES weak lensing, you go from the blue to the black. So you get even more crushed down. So this shows you really especially for these additional parameters, the additional data really does help you. And if you turn on redshift space distortions, you go from that's hard to see here, you go from the black contours here to the dashed contours there. So the weak lensing here pushes you down. That's what we expect based on what weak lensing measures, and redshift space distortions constrains you in that direction, which again is what we expect because that's what redshift space distortions measure. And so in that sense, actually, constraints on these parameterizations are very easy to predict when you think about what the data measures. Okay, actually maybe I have time to talk about one last thing, and this is the integrated Fitzhoof effect, which is not a very powerful data set, but it's actually kind of nice. So I already mentioned that we see this ISW effect, but this is actually also a nice data set, because you remember in the beginning I said maybe we don't understand something, and this is a fairly direct test of acceleration. And so the ISW effect, when you calculate the temperature perturbation, then you have a term that is the integral of this should be a plus in my notation, I'm sorry, this is a different notation, of the time variation of phi and psi. And basically what does this do? It's the case when you have some potential well, and so your photons drop into the potential well, and what happens to them when they drop into potential well?
They're coming together.
Yeah, but to their energy?
Gravitational redshift.
Yeah, actually blue potential well doesn't change. But if the potential well changes, let's say it becomes deeper, then the photons get the blue shift as they fall in, but then the potential well gets deeper, so they have to climb out from a deeper well, and so they get more redshift than they got blue shift, and so you get an overall shift, and that's why it's the time variation of the potentials that is important. And then there is a coincidence that when you look at the Poisson equation, so let's look at the time variation when we are in matter domination. The Poisson equation was 4 pi g a square rho matter delta matter. Okay, and so the rho matter goes like a to the minus 3. Here we have an a squared, so we have a squared a to the minus 3. This combination goes like 1 over a. And during matter domination, the structure grows exactly like the scale factor. So delta grows exactly like a. So you have a squared, a to the minus 3a, and so this is exactly constant. And so in a matter-dominated universe, your gravitational potentials stay exactly constant. And so you don't get an ISW effect because the photons climb out of the same potential depth that they fall in. But when you start to accelerate the universe, so the expansion of the universe, then the additional expansion kind of now with hand waving drags the potential well like apart and makes them less steep. So effectively the growth rate here becomes less than a. And so now you start to generate the phi dot. And so in an expanding universe, in a universe with accelerated expansion, you now start to generate this ISW effect. Now normally this ISW effect is hidden inside your CMB, and you cannot easily extract it, but it comes due to the potential well. And so when you look at the cross correlation between a tracer of your structure and the CMB, then this cross correlation will reflect this ISW effect. And so then you can go and look, do you see an ISW effect or do you not see an ISW effect? And here is 2015 data. And okay, because I'm hiding it, so normally this shouldn't be there. But here you can see some examples. So here is your tracer of the structure, and here is different combination of Planck data, and I will tell you a bit later why there is such a complicated table here. And so this, for example, is lensing data, and normally we use SMICA, I think, for example. And so you can see that, but generally you can see there is like a 30% error, but it's around 1, and if the combination of all of them is suspiciously close to 1, and has about a 25% error. So that's about a 4 sigma detection of a non-zero ISW effect. And then you can translate this, you can make a likelihood, and you can try to measure omega lambda and W. And personally, I really don't believe this precise peak at -1. But okay, the takeaway is that this is a very model-independent test of the accelerated late-time expansion, and it's really consistent. And the reason why there is such a big table is that for a long time people got a much too strong ISW effect, and but now with the newer data, it's actually exactly in line. So that's maybe another lesson. So for data that is not very good, you get sometimes really big statistical outliers, so you have to be careful. Okay, good. So I'm actually slowly getting to the end, and so this is just a reminder. Then again, for the observational side, I mean, the key takeaway is that you really want to combine these two probes. So you want to combine lensing and redshift space distortions, and this helps you to tell apart the two potentials. When you know the two potentials, that's really what gives you constraints on your modified gravity and dark energy models. Okay, and then I'm effectively at my final summary. So what did we discuss? So we saw that the standard lambda CDM model very long time ago on Monday, we saw that we have a homogeneous and isotropic background metric. So it seems obvious, but let's not forget that we have this assumption always in the background. Then we have a dark matter and cosmological constant, and at least this is exactly what we want to test. And there are other ingredients, and in principle we should always test all of these assumptions. So we really have to be careful. We focus on this, but we shouldn't forget that there are many other assumptions in our model. And so the goal then, looking at this seems to fit. Okay, we want to test whether this fits the data, and we also want to test. Okay, but we have the problem that we don't understand why there is such a small cosmological constant. I mean, we are a bit in an unfortunate place where the theoretical models really predict a much larger cosmological constant, so large that the universe, the universe could exist, but we couldn't. So effectively, the predicted universe is impossible, and so then we have a tendency to say, well, maybe exactly 0 is preferable to small but non-zero, and so we then pretend that we can totally remove a cosmological constant, but then we have to add in something else. Okay. And then we want to test, just more generally, we want to test or measure the physical properties of whatever does the acceleration with the physical properties of whatever is accelerating the expansion rate, and then we can also check if it's consistent with the cosmological constant. But because there are so many different models, I personally think if you want to come from the observational side, you really want to use these large classes of models, so effective field theory or the phenomenological models. If you come from the theory side, of course, then you would like your fundamental theory to give to you a precise model, and then you can compare that to data. Unfortunately, a very long history of research in that direction has not been very successful. So me personally, I'm much more now focusing on observations and trying to come from that side and hoping that we see a deviation, not that we were much more lucky with that so far. Okay, then some of the things that I didn't talk, well, I talked a little bit that there are non-cosmological probes as well. So that, for example, impose screening, so solar system tests, stellar structure. There are stability issues that your models need to satisfy that I also didn't go too much into it. One point, though, that is now really becoming more important is that most observations, they will go quite deeply into the nonlinear, into the regime of nonlinear structure formation. And so we need, for all of these models, we need to somehow understand nonlinear structure formation. So this is at the moment considered as one of the main problems that we are going to have. I mean, it's even difficult for the next generation of surveys like Euclid or LSST to understand this at the level necessary for a cosmological constant. We are definitely not going to understand it for 50 different fundamental models. Maybe we can understand it for the effective models, but this is now a big effort and it will be very difficult. And so the summary of the observational situation at the moment is unfortunately quite easy. There is no clear indication of any deviation from lambda CDM, and there are some smaller ones, and I think probably all the cosmologists agree that the biggest of these smaller deviations concerns the Hubble parameter, which has a relatively large difference. So statistically, there are the different measurements are not compatible, but the question is whether this is a systematic or a physical effect. But the problem is a bit here. There are not really good physical effects. If it was the lensing, then we would say, oh, we know exactly what can explain the lensing, and then we would be much happier to conclude that we see something funny. If it is the current expansion rate that is very different, but at higher redshift not, then it's a lot harder to say what would do that. Okay, so this is roughly what I hope I explained in a semi-understandable way.